Alright, this is part 2 of our 2-3 lesson, where we are talking about the product and quotient rules and higher order derivatives. 5 in your notebook, we're going to have f of x equal 3 minus 1 over x all over x plus 5. And we want to find f prime, and we want to write the equation of the tangent line at the point -1, 1. So let's first start by finding the derivative. And in order to do that, let's clean up the function a little bit. I'm not a big fan of having fractions within fractions. So let's get rid of that denominator of x in 1 over x. And what we'll do is we'll multiply everything in the equation by that denominator. So we're going to multiply everything by x. What that's going to do in our numerator is allow us to rewrite it as x times 3 is just going to be 3x minus x times 1 over x is just going to be 1. So our numerator is going to be 3x minus 1 over, and then we distribute the x in our denominator. X times x is x squared, plus x times 5 is 5x. Now we can find the derivative. And if we're thinking of that quotient rule, we could let our numerator be our f, even though the entire function is, and our denominator be our g. We need to figure out what is f prime and g prime, as in what's the derivative of the top part and the derivative of the top, which maybe instead of calling it f, we call it t this time for top. T prime is going to be just 3, and then we find the derivative of our denominator. G prime is going to be 2x plus 5. Now we use our quotient rule. So we're going to take g, our denominator, so f prime is going to equal x squared plus 5x times the derivative of our numerator times 3 minus our original numerator, 3x minus 1, times the derivative of our original denominator, 2x plus 5, and that is all over our denominator, x squared plus 5x squared. So let's clean it up. In fact, I'm going to clear my screen and just have my f prime part at the top. Alright, so let's, in our numerator, distribute this 3. So we're going to have a 3x squared plus 15x minus, let's FOIL what we've got in this second part. 2x times 3x, that's 6x squared. 2x times -1 minus 2x. 5 times 3x plus 15x 5 times negative 1 minus 5. Now, we put all of that over x squared plus 5x, quantity squared. We can also distribute this minus sign once we've combined any like terms in our red part, which, let's do that. Let's combine the like terms first. We've got negative 2x plus 15x. That's going to make a plus 13x. So we'll have in our next line 3x squared plus 15x minus 6x squared plus 13x minus 5. And when we distribute this minus, that's just going to change the sign of everything in the parentheses. So our numerator is going to look like 3x squared plus 15x minus 6x squared minus 13x plus 5 all over x squared plus 5x quantity squared. Now, in our numerator, let's combine like terms. We have a 3x and a negative 6x squared. 3x squared minus 6x squared gives us negative 3x squared. We have a 15x minus 13x, so we're going to have plus 2x, and we've only got the one constant term, 5. We can leave that over x squared plus 5x quantity squared, and that is fine with me. If you want to multiply it out, we can do that as well. But I'm not going to worry about expanding mine out because they asked us to do one other thing in this example, and that's write the equation of the tangent line at the point negative 1, positive 1. So if we want to find the actual slope at the point negative 1, 1, we're going to plug in negative 1. Figure out what do we get from that. Or in fact, we know it's going to pass through that point. Not that that point is on our original function. So we're going to take negative 1 and put it in for x. We're going to have negative 3 times negative 1 squared plus 2 times negative 1 plus 5 over negative 1 squared plus 5 times negative 1, and that quantity is squared. If we square a negative 1, we get 1. Negative 3 times 1 is just negative 3. 2 times negative 1 is going to give us minus 2 plus 5 in our numerator. In our denominator, we're going to have 1 minus 5 quantity squared. And I actually noticed something. I noticed my numerator, negative 3 minus 2 plus 5, that equals 0. And I also noticed that my denominator is going to end up being negative 4 squared. Well, it doesn't really matter what negative 4 squared is, because we're just going to get 0. So that's the slope. Which means, if we were to plug all the information we know, an m and a point, into, say, y equals mx plus b, the slope-intercept form, we know a point. We've got 1 equals m is 0 times negative 1 plus b. Well, b is going to just equal 1, and if m is 0, that means the slope, or not the slope, the equation of our tangent line is just going to end up being y equals 1. This is the tangent line. So we found the two things they asked us to find. We found f prime, and we found the equation of that tangent line. Let's move on. A little thing I want you to take note of is that not all quotients need to use the quotient rule. Sometimes we could rewrite the original equation and we won't even have to use the quotient rule. We might use a different rule like the product rule or something else we've learned. So let's look at some examples of quotients where we don't need to use the quotient rule. So we'll call this example 6, and I've got 4 parts to this. We're going to have part A, y equals x squared plus 3x, and that's all going to be over 6. Well, how about instead of using the quotient rule to solve this, we rewrite this as 1 over 6 times x squared plus 3x. We can decompose it. So if we want to find the derivative of this, well, that 1 over 6, that's just a constant multiple. So we're just going to find the derivative of what's in the parentheses. We'll bring the 1/6 through. The derivative of x squared plus 3x, well, we have learned a lot of different rules for this. We can bring down the 2, so we'll have 2x plus 3. I'm fine with you leaving it this way. I am also fine with you rewriting this as 2x plus 3 all over 6. So rather than use the quotient rule, we simplified it. We made it easier. Let's see another one. So this is example 6b. We're going to have y equals 5x to the 4th over 8. And instead of leaving it like that, let's make it 5/8 times x to the 4th. Well, the 5/8, that's just a constant multiple. So we'll go y prime equals 5/8 times the derivative of x to the 4th is going to be 4x cubed. So let's multiply that out. 5/8 times 4, which we can write 4 as 4 over 1. The 8 and the 4, they simplify. 4 turns into 1, 8 turns into 2. Which means our derivative is going to end up being 5x cubed over 2. There we go. Let's look at the next one. So 6c, we're going to have y equals -3 times 3x minus 2x squared all over 7x. So let's actually rewrite this as -3 over 7 times 3x minus 2x squared over x. That's fine. It's just undoing some multiplication of fractions. If we do that, then y is just going to be -3 over 7 times, well, the x's in that other part can simplify. So we're going to have 3 minus 2x. We can treat the -3 over 7 like it's a constant multiple. So y prime will bring the -3 over 7 through, but we're going to just be multiplying it by -2, the derivative of what's in the parentheses. So y prime is just going to be 6 over 7. Let's look at 6d. In 6d, we're going to have y equals 9 over 5x squared. Well, let's rewrite this. we can rewrite this as 9 over 5 times x to the negative 2. Well, y prime's not going to be that bad then. We'll bring 9 over 5 through. The derivative of x to the negative 2 is negative 2 x to the negative 3. Which if we bring everything through, multiply what we've got, we'll have negative 18 x to the negative 3 over 5. But we don't like that negative 3 as a power. So we'll bring it down. We'll have negative 18 over 5x cubed. And we found y prime. Let's look at the next theorem we have in chapter 2. We've got theorem 2.9, which are derivatives of trig functions. And in an earlier lesson, our last one, 2.2, we looked at derivatives of the sine and cosine function. Today we're looking at other trig functions. So, we can say if we have our function y equals tangent x, then y prime is going to be secant squared x. If we have the function y equals cotangent x, y prime is going to equal negative cosecant squared x. If we have y equals secant x, the derivative of that will be secant x times tangent x. And if we've got y equals cosecant x, the derivative will be the negative cosecant of x times the cotangent of x. So we're going to use those in our next example. Example 7, we want to find the derivative of, in part A, y equals x minus the tangent of x. So we've got a difference rule here and a trig deal. So when we're finding y prime, we remember in the difference rule, take the derivative of the first and then the derivative of the second and use the difference of them. Well, the derivative of x is 1 minus, based off of our last theorem, the derivative of tangent is secant squared x. And then we've actually finished it. Let's also look at another one in this example 7. We'll have y equals x times the secant of x. So that's a product rule, which we've learned about in this lesson. We write that as the first times the derivative of the second. So x times the derivative of secant x is secant times tangent plus the first secant x, I mean the second, not the first, times the derivative of the first, and the derivative of x is just 1. So I'm not going to worry about writing that. I'm fine with you writing this as your answer, but I also notice each term has a secant x, so we can take that out. So y prime could equal secant x times x tan x plus 1. And we're going to wrap up this video.